Hi, my name is Cadet Frankie Whalen.
My name is Cadet Adam Hug.
In this video, we're going to show you first why we think proofs are different from other kinds of math we've done in the past, and secondly, we're going to take you through a formal proof of a problem we were given to show. So the example you can see on the video on the board is what we're going to use when we talk about why we think proofs are different from other kinds of math. So first, to go through this proof, the problem statement is let x be in z, then 11x minus 7 is even if and only if x is odd. Our formal proof or answer for that is that there are two implications to prove. First, if x is odd, then 11x minus 7 is even. And second, if 11x minus 7 is even, then x is odd. We begin with 1. In this case, a direct proof is appropriate. Assume x is odd, then x equals 2r plus 1, where r is in z. So 11x minus 7 equals 11 times quantity 2r plus 1 minus 7. As you can see, eventually comes out to 2 times quantity 11r plus 2. And since 11r plus 2 is an integer, 11x minus 7 is even. We now prove the second point, which is the converse of 1. We use a proof by contrapositive. Assume x is even, then x equals 2s, where s is in z. Therefore, 11x minus 7 is the same as 11 times 2s minus 7, which comes out to 2 times quantity 11s minus 4 plus 1. And since 11s minus 4 is an integer, 11x minus 7 is odd. End of proof. So our points, going back to why we think writing proofs is different from other types of math, is we start with that we think writing proofs has a big emphasis on communication. You can tell right away from the amount of words on the board there in this answer. So starting with the problem statement, let x be in z, then 11x minus 7 is even if and only if x is odd. So the emphasis on communication here is shown in that there's an implication or two mathematical statements we have to prove just from the language of that problem statement, if and only if. And that emphasis on communication carries through in our answer, where we see beginning statements, beginning the paragraph, so to speak, with we begin with words like assume x is odd, therefore we now prove. So all these things are examples of why communication is important in the answer. Our second point is that answers are in paragraph form. So that's pretty obvious there. You can see the answer on the board, the formal proof, from where it says proof to where that block is on the end is complete sentences. We're using transition words, we're using filler words to make the proof flow, to make sure it makes sense when you speak it out loud. Third point, proofs are different because of notation. So not everything is expressed in words, even though there's an emphasis on communication and being able to read it. But there have to be symbols and definitions used that make sense to whoever the audience is for the proof. Examples of that are the definitions of odd and even. So we introduce some new variables with r and s, and then we use those definitions. Odd is 2r plus 1, and even is 2s. And that has to make sense in the context of the other variables we're working with, as well as what we're trying to prove. And you can see that the arithmetic works out there, and it helps us in our proof.
The next reason that we think proofs are different than normal mathematical problems is that there's more of an emphasis on logical reasoning as opposed to problem solving. So with a normal math problem, you're usually given a problem statement, and then you work through a few steps to get to a final answer. The difference here with proofs is that most of the time you're given the final answer or the result, and you have to backtrack and find out the steps in order to prove that result. So in actuality, it's more about the steps, ideas, and definitions that you use, the formal logic, as opposed to the actual answer that you get. So in the case of this problem here on the board, if it were more of a problem-solving type of problem, it could look something like determine 3 values of x that make the following statement 11x minus 7 even. So for this, you just have to plug in different values of x, and you would eventually find that 3 odd numbers could then make that following statement even. With proofs, though, we have to prove that x is going to be odd every single time for this case. So you have to use logic, reasoning, and definitions and know how those theorems work in order to reach that final conclusion. The next reason that we think proofs are different is that they're more abstract and there's usually not just one right answer or method to solve the problem. So for this proof, we used a direct proof for the first part and then a proof by contrapositive in the second part. But we could have easily used a proof by contradiction. What this would have looked like is assuming to the contrary that x is equal to 2s. If we plug in that value, 2s, in for x, we would find that the following statement would equal 2 times the quantity 11s minus 4 plus 1. This would mean that the statement is odd, and it would lead to a contradiction. So as you can see, there are multiple ways to solve proofs, and that's just another reason why it's different than normal mathematics. And then finally, you have to write proofs in a way that is easy for someone who has never seen the problem and make it easy for them to understand. So this is why using that logical reasoning, making sure you write out all definitions and all theorems you use is really important because it should be understandable to someone with no prior knowledge in the subject. Now we are going to explain to you the steps to writing proofs. The first part is the know. This is where you write down any variables, functions, or restrictions that were given to you in the problem statement. The second part, your show, is the result that you're looking to prove. The third part, expanded know. This is where you begin to write down the definitions and theorems that you're going to be using to solve the proof. The fourth part, expanded show. This is where you use your theorems and definitions to begin your preliminary proof methods that you could use to solve the proof. The fifth part, scratch work. This is where your formal logic comes into play. You can begin to simplify and modify the variables and functions that you're given in order to reach the desired conclusion. The sixth part is where you actually will write your formal proof. This is where you build on the scratch work, add in your filler words, and make it into a logical paragraph that is easy to follow. Before we solve the problem that we were given, we want to go through the proof method that we used to solve it first. We used a delta epsilon proof method. This uses the definition of a limit. It says the limit of f of x as x goes to a equals L if for every real number epsilon greater than 0, there exists a delta greater than 0 such that for every real number x with 0 is less than the absolute value of x minus a is less than delta, it follows that the absolute value of f of x minus L is less than epsilon. In other words, we use a chosen value of delta to say something about our real number epsilon to show that the limit of f of x equals L.
Our problem statement, starting in the top left corner of the board, is let the function g from the set of all real numbers to the set of all real numbers be a bounded function where the absolute value of g of x is less than some positive number b. And we suppose that the function f, which also goes from all reals to all reals, and we have a is in the set of all real numbers such that the limit of f of x equals 0 as x approaches a. What we're trying to prove is that the limit of f of x times g of x as x approaches a equals 0. Going through our stepwise process to solving a proof, we start out with our know, which is that g is a bounded function, f is a function, and the variable a is in the set of all real numbers. Our show is that pulling from the end of the problem statement, the limit of f of x times g of x as x approaches a equals 0. Expanding our know, we have that right there from the problem statement, absolute value of g of x is less than b, And because b bounds g of x is the upper bound for g of x, we can say delta for g of x equals b. Again, we have limit of f of x equals 0 as x approaches a, and since this is a delta epsilon proof, epsilon is greater than 0. For our scratch word, if the absolute value of g of x is less than b, then b is greater than or equal to 0. If b is greater than or equal to 0, then epsilon over b must be greater than 0. And that comes from, in an epsilon delta proof, we must choose a delta that is dependent on epsilon. So epsilon over b is greater than 0. And we use that as our delta for f of x, which means that 0, which is less than the absolute value of f of x minus 0, is less than epsilon over b. Going up to the top right corner of the board, 0 is less than the absolute value of f of x times g of x minus those two limits, which is 0 times a, which is less than those two functions' delta values, which is epsilon over b times b, which reduces to the next step there, just epsilon on the right side.
So now we use the work that we had in our scratch work to write out our formal proof, which is in paragraph form. So let g be a bounded function such that the absolute value of g of x is less than b, and let f be a function such that the limit of f of x as x approaches a equals 0. And then finally, since this is a delta epsilon proof, let epsilon be greater than 0. Since g is bounded and the absolute value of g of x is less than b, then b must be greater than or equal to 0. Thus, epsilon over b is also greater than 0. Because the limit of f of x as x approaches a equals 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus a, which is less than delta. And then, substituting in the values, 0 is less than the absolute value of f of x minus 0, which is less than epsilon over b. It then follows that 0 is less than the absolute value of f of x, which is less than epsilon over b. And then pulling from what we had in our scratch work up in the top right corner of the board, we can see that this final statement reduces down to the absolute value of f of x times g of x is less than epsilon, which is the statement we were trying to prove.
The second part of that last problem statement asks us to use the previous result to determine the limit of x squared times the sine of 1 over x squared as x approaches 0. So what we're going to use from the last problem, our answer to the last problem, is that we know that the limit of f of x times g of x as x approaches a equals L times m, which represent the individual limits of the function f and the function g. So we can split up our problem there into two different functions, f and g. The first function being x squared, and the second function being the sine of 1 over x squared. Since the limit of f of x as x approaches 0 equals 0, and we know that from just plugging 0 into f of x for x, 0 equals L in the statement we have above, and the limit of the entire f of x times g of x equals 0 times some limit for g of x, which ends up being 0.